So welcome back to the course page on microprocessor. Our discussion is on digital to analog converter DACs, and in the last class we discussed one type of a digital to analog converter. So the main purpose of a digital to analog converter is to convert the digital values into its corresponding analog voltage, and that analog voltage V out is proportional to the digital value. So one of the method for converting a digital signal into analog signal is by using a binary weighted resistor method, and we have shown how to convert a binary digital data into an corresponding analog by using an operation amplifier and a series of weighted resistors. So that's one of the methods that we employed in the last class. So in that case, our output voltage V out is equal to the total current, sum of the current into the RF, and whenever the RF is equal to R1, then we can use this equation as it is equal to V reference into the B3 plus B2 by 2 plus B1 by 4 plus B0 by 8. So we can nicely calculate what will be the output voltage corresponding to a binary digit. And one of the major difficulty with these binary weighted resistor is that we require a highly precision resistors. And again, if the number of bits increases, then the resistor values, the weighted resistor will increase further. So that will make some difficulties, and moreover it becomes a more expensive one. So that's why we use a different approach. So in the binary weighted method, we used this type of a signals, that means R-2R, 4R, 8R, and instead of using this network, we use a R-2R ladder network. Then here this is the D0, this is D1, this is the least significant bit, and D1, D2 and D3, which is known as the most significant bit. Then what happens is, and if you connect a operational amplifier to this network, this ladder network, we'll call this network as a R2R ladder. Then what happens is, when the D0 bit is 1, then it needs to go through this interface. That means it needs to go through all these resistors, and the current becomes very low. And compared to that one, then here in D1, in D3, here it requires only to go through only this part, only through this R only. So that's why the fraction part is much higher compared to the D0. Its contribution by the D3 is much higher. That's why we called this bit as a MSB, or the most significant bit. So this is one of the best method to implement a digital to analog converter for higher bits. So this is how we can redraw the diagram in a different way. This is MSB, and this is the LSB, and you can easily understand by using wherever the ground path is, then you can say this is the LSB, and here this part is the MSB. So again, look through this diagram, then if you want, you can use the switch to switch the signals. Say for example, in this case this is equal to 1 1 1, then the this least significant bit, the current through this least significant bit needs to pass through all these network, and whereas the most significant need requires to pass only through this R only. And so we can just rearranging the circuit, then instead of using this weighted resistor, we can use a R-2R ladder by using designing a digital to analog converter. So the less significant the bit, then the more resistors the signal must pass through before reaching the op-amp. It requires to pass through all these resistors. So in every step, then the current is divided by a factor of 2 at each node, and that's why we use this, how we can understood the most significant bit and least significant in case of digital to analog R-2R. This is a more illustrations are given here. Now let us analyze the circuit. Suppose I have given a 0 0 2. The pattern is 0 0 2. That means here it is 0, here it is 0, and here I have connected the reference voltage, so this becomes 1. So this voltage, the current through this one needs to pass through first resistor network, then it requires I divided by 2, then again the current divided by 2, then again the current divided by 2. That means the contribution by the B0 bit is very negligible, and that's why it will call it as least significant. Its significance is least. So the total voltage, output voltage, we can calculate the output voltage as V out is equal to the RF by R into V reference of B2 by 2, B1 by 4, and B0 by 8. So this is the equation that by using this equation you can easily calculate the output voltage, analog output voltage, by using the digital to analog in a digital to analog converter. And if you want, you can do one problem there, then we will understand the concept in a much broader sense. Suppose the input is equal to 101, it's a digital input is 101, and the reference voltage is 10 volt, and we are using R as a 2 ohm and RF is as 2R. Then let us see the output current. I0 is equal to minus V reference divided by 2R plus 2R. 1 2R is here, this is 1 2R. These 2R and 2R are parallel, and this can be added with 2R plus R. Here it is an R plus R. That's the current, and that is equal to some around minus 0.67 milliampere. And another contribution is from this guy, that means this is B2. B2 is its contribution is only half, so that's equal to I0 by 2, and here it is I0 by 8, and V out is equal to op-amp current through the op-amp into the RF value. So we'll get the output voltage as 4.17. Those are the two types of weighted binary. So let us analyze the pros and cons of these two methods. And binary weighted is easily understood, but in the case of an R-2R, only two resistor values are, we need to use it only two resistor values, and it's easy to implement, very easy to implement, and also it's very easy to manufacture, and it has a faster response time. And but if you consider a weighted binary weighted resistor methods, it's only limited to 8 bits resolution, and it requires a large number of large values of resistors. Also it require highly precision type, and moreover it's much more expensive, and the greatest possibility to make some errors. And but in case of an R-2R, it is more confusing. If you are analyzing the system, it becomes more confusing. So those two are the methods that we normally use for the digital to analog conversions. And next, tomorrow we'll discuss about the performance specifications of these digital to analog converters.